So Sigrid's originally from Norway, from Trondheim, and did his first degree in electronic engineering in Imperial, and then went to Edinburgh to do a PhD in informatics. I think she's going to talk about that work in particular. And then now is at Norse in Bergen as part of the climate risk group. So that's obviously where the alignment with our work comes from. So thank you.
Yeah. So yeah, I'm going to talk mostly about stuff from my PhD and try and make it sort of from a user perspective. Why should you care about this? Why could it be useful? And then I'll talk a bit about ML downscaling. One of the applications I had in my PhD was air pollution monitoring. This is an air pollution monitor. So there's some scattered images that I used to enliven my talk as we go. This is the one that we've already done. Doug is recording it. There's going to be two parts. So it's going to be sort of split. Do the first part, any questions about that? Then there's a second unrecorded part of the work that's in progress. Doug mostly did this, but I work at Norse. I also affiliated with the Björknes Center in Bergen, which is this umbrella organization between Norse, University of Bergen, the Nansen Center, and the Institute for Marine Research. Before that, I was at Edinburgh. I did a PhD in informatics, and then electrical electronic engineering. And that's sort of my big city, slightly smaller city with a hill, even smaller city with even more hills. My evolution. So another air pollution monitor. The talk is going to be mostly about hyperparameter tuning. I'm going to introduce what it is, why we care about it, then do some practical advice, sort of even if you don't really know what's happening, what can you do, and then go a bit under the hood, what are those methods you're doing, and then even more specifically talk about one of those methods, which is what I mostly worked on, which is Bayesian optimization. And that constitutes the first part, and then we can wrap that up, and then I'll talk a bit about the downscaling project that we have that's called EAGLE, where we're downscaling some weather data. I'm also happy to be sort of stopped and take questions. If I'm using lots of terms which no one understands, it's not very helpful to anyone. So, yes. But I think you might be recorded. So, what are hyperparameters? If you have a machine learning model, this is my very simple neural network. Data comes in here, moves through the network, and comes out here. And then we have decisions or tuning that we need to do on two different levels. So one of them is tuning the parameters of the model, so the weights. So that is, a number comes in here, we multiply it by something, add something, have a nonlinearity, and then we keep going on. So for those weights, it's relatively simple. We can look at the gradient and change those values to move down in the optimization landscape. For that is our inner optimization problem, because there's also an outer one, which is how many of these layers should I have? How big should they be? How quickly do I adjust the parameters? And those are all hyperparameters. And that's what I'm talking about when I'm talking about hyperparameter optimization. And we need a different approach to that. So some examples would be input batching. So often we will not show our neural network all of the examples at the same time, but we also don't want to show it just one by one. So how many of those examples do we show? Maybe we need to do some data imputation if we don't have a nice, entirely clean data set. Then what kind of layers are we using? How big are these layers? How many of them do we have? And a bit of the nonlinearities that we have between them. So again, how we're setting up our network. And then on the training side, you have which loss function do you use? How do you regularize the data? So what choices do you make to avoid overfitting? And then what learning rate do we have? How quickly do we change the weights in our network? And you have two related concepts here. There's hyperparameter optimization, and you also have something called neural architecture search. And I'm just kind of considering them as similar topics and not putting like a hard line between the different ones. But if you're going sort of far into the like, what is my architecture, you're probably more talking neural architecture search. So I guess question one, do they matter? Yes, they do. So this is some work that was led by Tom Lee, and we looked at a specific setup which is called continual learning, and we looked at some hyperparameters of those algorithms and also on the learning rates. And then we randomly sampled those hyperparameters, trained the networks, and looked at how accurate they were. And we can see here this spans between, on some different data sets, a span of about 10-15% of accuracy. So that could be a bit, the difference between this works well enough or it doesn't work. And if you're comparing to someone else's network and trying to get state-of-the-art results, this would be a massive difference. So what do these optimization landscapes look like? This is simplified into 2 dimensions, but you probably have some which make very little difference. That would be the one along sort of y-axis here. And then some that do matter would be the x-axis. So the problem is both figuring out what values you want and also figuring out which of these parameters are important or hyperparameters are important and which ones are unimportant. And it gets harder because the evaluation is noisy. You're training a network and there's stochasticity to that process. It's non-convex. This is just 2 dimensions. You're actually doing this in many dimensions. And it's opaque. It's quite hard to reason about. If I change the learning rate, what is that going to change to my downstream accuracy? Just going through quite a lot of processes. And here's just sort of more like a real life example. This is really in 4 dimensions, but I plotted 2 of them. And we have, especially this type of parameter is sort of the expressivity of the model. So sort of how complex a relationship between the input and output can you represent. And so we see that for this example where we have very little data, we are looking for these different points which show those are the 10 best that we can get. So it's not the easiest landscape to explore, finding those settings. So how would you go about it? There's option 1 and option 2. Option 1 is you do it yourself. And then you kind of just have to be systematic about it. And what you end up doing is doing the reasoning yourself about if this learning rate worked well and this slightly smaller one didn't work as well, then I'll try a slightly higher one. But then how does this interact with when I change the model size or I change the data? So I would advocate option 2, which is you automate it. And so there are multiple softwares that can do this for you. And the advantage then is that you can focus on other tasks. And often the loop of the training the network is sort of long enough that you're going to have to do the context switching as well. Like you can't be doing this full time. You set it off, you start doing something else, and then you have to go back and be like, what was I thinking when I chose this? What is the next one I should try? So I think automated software is the way to go. And there's some basic principles. So one of them is computers are quite good at tracking many experiments at the same time. Instead, like managing to keep many numbers in their head at the same time. Another one, which is what's illustrated here, is that some options just don't work very well. So here is a method where we start off by training for just a small budget, a lot of different options. And then we take the half of them that work the best, and those are the only ones that we continue with. And we can do this because we can stop and start by saving what the weights are in our network. And so in that way, you're not guaranteed to find the best one, because maybe this one was going to like plummet and then do like this, but probably you're finding quite a good one. And you can do that much more efficiently than trying all of them. Another thing we can do, and that's the one we're going to talk most about, is use other ML models to predict how well your hyperparameters are going to work. And a different concept, which we're also going to keep coming back to, is we can learn between different projects. So we're not starting from scratch with our search for a good learning rate every time. We're seeing this one worked quite well previously. Let's try that one again and let adjust around the values we found. That was the very sort of motivation for what hyperparameter tuning is. Then by tuning hyperparameters 101, it sort of comes down to some basic steps in deciding which ones that we want to tune, deciding which values are acceptable, picking how you're going to automate this, which method you trust, which framework, drink some tea, and then hopefully enjoy your improved model. So none of these points I really have like, this is the like entire list, but these are more like thinking points, I guess, for each of them. So in terms of which ones you have to tune, you kind of have to see a bit which ones seem the most relevant. You can see at what other people are optimizing, which ones are exposed in the implementation. That's a good indication that one, people don't think there's a set one in stone. Try a few different ones, see which ones have a big impact, which ones don't have a big impact. Also, if in the papers people keep mentioning we use this specific batch size or learning rate, that's an indication that they thought this was an important thing. And then also just these hyperparameters, they could be continuous, they can be discrete, they can be categorical, they can be binary, and the frameworks all know how to do this under the hood. And then your search space, what values you permit. Again, have a bit of a look at like what other people use. But also you can start wide and then narrow down. And then you want to think about the scaling. So for the learning rate, for instance, which maybe we go from like 10 to the minus 3 to 10 to the minus 6 or something, we don't want to do linearly sampling that value. We want to sample in the log space, so you're looking at the different magnitudes of what that value could be. Then methods, we're going to talk more about that in the next part, about under the hood, but you can just randomly pick them. You could try sort of systematically trying combinations of values in the grid search, or you can do something smarter. Then there are several frameworks. All of them are good. So I'm just sort of listing suggestions. I've contributed to SignTune, so I quite like that one. There are other ones that's probably more on the like research side for hyperparameter optimization. There are other ones which are better or have more work on the visualization side. Pick how you're training, validating, testing your method, and which metric you choose from or you care about. Yes, so in the libraries, SignTune, I think, has a better spread of transfer learning than some of the other ones, but people like all of these, and all of them are better than doing it by hand. If you want to drink some tea. Yes, I mean that sort of is the pitch of like, this is something we care about. There are libraries to do it. You need to do some of the setting up of the experiments, but then it will do a lot of it for you. So then, hopefully you're also curious about what happens underneath. So I mentioned a list of motivations for why it would be good to automate it, why we think computers could be good at this. And so for each of these, I'm kind of going to use them as an excuse to introduce some different methods. So computers are good at tracking many experiments. So maybe we don't need to adapt to what those experiments are like. We just need something that actually keeps track of it all. We can discard some early on. That was the curve I showed about cutting things, or like dropping half of them for every time we increase the amount of training. Bayesian optimization comes in when we're predicting how well the hyperparameters will work. And then transfer learning is that we can learn between different projects what kind of hyperparameters work well. So 2 different methods for no adaptation. One is grid search. So then for all the hyperparameters, you pick the values which you think or like, you break up your search space, and then you try all of these combinations. And that puts quite a limit on how many values you can try for each of them, as this grows very fast. Therefore, it's turned out that random search actually works a bit better. And then you just pick at random from all of these. And the advantage here is that you're actually trying, 9 different values for the parameter, hyperparameter. That does matter. And so in this example, for illustration, we are actually able to find the bottom one here. But both of these are just like you set it up, and then either systematically or more randomly, you sample within the search space. And so the advantage really just is it's automated. You're not sitting there doing it. Then in terms of ML specific, the fact that it isn't really a black box, we have some idea about what's going on inside of the box that we're optimizing, means that we can exploit that. So here we have successive halving, which I described about. We have 8 different hyperparameter combinations which we try. We throw out the 4 that work the worst, train for twice the amount of time, throw out, keep training. And then learning curves, I didn't add a figure here, but what we're doing there is, once we've gotten here, we can have a simpler machine learning model which tries to predict what the curve is going to do. So instead of just ranking these, we will make a prediction about how we think it's going to be progressing. And based on how we think it's going to be progressing, we decide which ones we want to keep and which ones we don't want to keep. So it sort of becomes like, for this one, for instance, you probably see, oh, it looks like this one has flattened out, so we think it's going to flatten out. While for this one, maybe we think, oh, that one is still coming down. Then Bayesian optimization is this framework where we use machine learning to do optimization. And so here we have a Gaussian process or some other probabilistic ML model. And we use this to model a relationship between our input, which would be our set of hyperparameters, and our output, which is the accuracy of our model. And then we use this in an acquisition function to choose what input that we want to try next, which hyperparameters do we try next. And by measure real world here, I mean go like set up a training and see how well that works. So I kept sort of trying to describe this as I was writing up my PhD to one of my colleagues, and he was just at the end, he was like, so it's trial and error. And it is trial and error, but it's automated ML-driven trial and error. And it's quite popular for hyperparameter optimization. And we're going to loop back to this one as well, because it's my favorite one. And then transfer learning, the motivation here is that there's quite a lot of similarity between different problems about which hyperparameters are going to work well. So this is a slightly specific setup, but where here we have the same model, and we have a larger and larger set of training data. And then we have those same hyperparameters. I think I showed you this figure earlier. It was quite spread out where the best values are. So these are the 10 best ones. Now you can see that there's like a gradual change here, and they're collecting together. But also, if you choose some values which worked well here for number 8, they're probably going to work quite well for 15 as well. And it's even more so for those in between. So the motivation here is when things are this similar, we can do things a lot faster than starting from scratch. And this is like, this data set is a subset of this one, but it also holds for when they are same model, for instance, but different data sets, as long as they're sort of similar in terms of the size of the data. And so there are different approaches to it. The one which I just showed you is more about ordered transfer, where we think we have a sequence of these optimization problems. So like we're gradually increasing the amount of data. And so we think the most recent one is the most relevant, but we think the other ones are also slightly relevant, or are somewhat relevant as well. So that's what I'm illustrating here with like, for normal transfer learning, the arrows are all the same and we have to figure out which ones are most relevant. But here we kind of know in advance that the last one is going to be most relevant. Other approaches would be looking at the metadata. So that would be like, how many training examples do we have? How many features does the training data have? And then based on that saying, if it has similar number of data points, similar number of features, then we think that's most relevant to learn from. Or we can do something correlations, where like we try a few different hyperparameters and then see whether sort of the response that we get to those hyperparameters, which of the previous problems we've solved does this look the most like? So you would have, maybe you have one which like it turns out high learning rates worked really well, like that was one past problem you solved, and then one where really small ones worked really well. And then you try one high one and one low one for your new problem. It turns out the high one works best. Then you think you're most related to that other one where you had that behavior in the past. And then you can look at what other hyperparameters worked well then. Questions? Oh, and this is my example showing that this actually makes a big difference. So the green curves here would be doing no transfer learning. And so here we're going up to 25 different hyperparameter configurations. And all of these ones at the bottom are doing different types of transfer learning. So this score, we want it to be low, and you can get to a much lower score early on if you transfer between problems.
How related to those problems have to be, though? I mean, you said sort of about problems in general, but
yeah.
Are you assuming the problems are somehow in the same family of problems?
Yes, I think the more, so, there we go. This was from that example I showed where like things are, the training data are derived like subsets upon subsets of each other. So then they are very related problems. So this is probably sort of towards the extreme end of how big of the difference you get. But it's been used much more widely than that as well. But like as long as you have the same model and similar sort of types of data, if you're using like image data, then I think it would be worth doing this. So back to the automated trial and error. What we're doing is, we're using the machine learning to do the learning from past errors and successes for us. And in general, Bayesian optimization is suitable when there's no simple expression. So like if we're optimizing x squared, for instance, this is way overkill to what we can do. We can solve that analytically. Also, when measurements are expensive, so you want this part of it to take some time because we are putting computational effort into these two. So, and if this one is very cheap, then we're better off spending more of our compute budget on trying more things. So it's when, if it's expensive to get another evaluation, then we can justify doing sort of a lot of thinking about what we should be trying. And it's an optimization method, so it works when we're trying to find a minimum or a maximum. So there are a few different models, or people have different favorite models that you put into this, but the most common one is a Gaussian process. It's also called Klieging. And so it's used for, what you do is you get a probabilistic model out of it, and what you give in is some assumptions about how different points will be correlated. And so when you have this model, you have your estimate both of like your mean guess of how well these hyperparameters are going to work, as well as an uncertainty bound. Then you give that to an acquisition function, and that's an automated way of balancing your exploration and exploitation. And hopefully the next slide is a figure. So this is what a Gaussian process looks like. You have a true function in black here, which we don't get to see. We have some samples from it though, which are these black squares. And then based on those samples, we make up our model. So the blue line here is our mean estimate of what we think the true function is doing. And then we have an uncertainty bound. And this is quite a well-fitted model, so we can see that the true function is within our uncertainty estimates here. And once we have that model, we can set up our acquisition function. And you have different choices. This is my favorite one to illustrate. And here you pick sort of your exploration-exploitation balance, like how many times the standard deviation you're going to follow. And then this function becomes my acquisition function, and where it's highest is where I'm going to sample next. So I say this balances my desire for finding a high value, but also wanting to learn more about what the underlying function is. And so we can follow that through. So here we have our model. We have, this really isn't legible, is it? We have a model. We have this dashed line, which is the acquisition function. We find the highest value. And then here we've sampled what that value is. So then we've updated our model. We have a better idea about what's happening. We have a new set of acquisition function values. We find the new highest one. We sample that. That updates what we know about our function. We get a new point, which we think is the most promising candidate for what's going to work well. That turned out to work pretty well, but now we think maybe up there is going to work. That didn't work so well, and by now we've basically solved the problem. We're going to keep sampling. Yeah?
Why is it the highest value, not the highest spread?
Why are we picking the highest value?
Yeah, to do the next sample, next acquisition.
So that's because what we're doing is trying to find where the maximum is. So we don't really care if there's a highest.
You're trying to find the maximum to cut the whole curve. Yeah. Okay.
Yes.
Yeah. So, which is your optimal choice.
Yes.
Yeah, I see. Yeah. So you don't care about the curve in the result.
Yeah.
Yeah.
You can have different balances between how much you care about the spread versus the maximum value, and the very related method of sort of with active learning, you would be going where the maximum spread is. But this one, because we've said sort of starting out that what we care about is finding the maximum, you could have very high spread, but if you're confident that it's a very high but low spread, then you don't have to sample it. So this is in one dimension, but what we end up doing is, for the hyperparameter optimization, is we set up these models and we run them in the many-dimensional setting and decide which values we want to try to find good hyperparameters. And this is also a simple version in that you have just one output dimension as well as one input dimension. You can also have multiple output dimensions if you care about multiple output metrics. And also that's a way of doing transfer learning. You have multiple and you're predicting sort of curves for both of your problems. So with transfer learning, we talked a bit about before, in general, it's most often used for like you train your neural network on one data set, and then you want to adapt it to being useful for another one where often you have less data. But in terms of Bayesian optimization, here we're using it for other optimization tasks. And then it sort of becomes a bit of a choice whether you call it transfer learning or meta learning. So this is a motivational example of mine based on the fact that we used to make jam when I was a kid at home. So what we're doing here is we're optimizing several different related problems for the tastiness score of our jam. And then you're trying to choose how much sugar are we putting into our jam. And we can imagine first that we only have this green curve. We have these evaluations of it. So we figured out what the best sugar content is for this jam. Then we find some yellow apples. And then based on only having this green curve, what do we try next? And we can see that we can even if we just started by trying this one, we would start off quite well. In terms of you don't have to start your optimization from scratch. And once you have enough of these different kinds of apples, you have a good idea about what's the different, like what the spread is of what are good sugar contents or hyperparameter values for optimization. And we looked at a few different ones. The one that's been most used would be direct transfer, where you have these related problems. You don't really know which ones are most related, but they're quite similar. So like something that works well for one of the problems is going to work well for another one. Not perfectly, but well enough that it's a good start. Then we have the ordered one, and here the corresponding hyperparameter optimization case was when we had the gradually increasing training data set. So here we should care most about what is the most recent one. So you can see there's sort of a shift in what works well and what doesn't work well. And then the final one that we had was prior transfer. And so the jam example is we have different types of fruit. So different types of fruit, you need different types of sugar. But the equivalent to hyperparameters would be if you have very different types of models that you're optimizing, or different model and data setups. But you still think that the response might be similar. So even if the optimal batch size is different, or the optimal learning rate, you think how sensitive it is to getting that right would be the same. And that one, for hyperparameter optimization, probably these two are the most relevant, and this one sort of comes in for some other Bayesian optimization applications. So that's work that we did for air pollution monitoring. That's what you get. So these are sort of examples of how you could go about solving these different types of problems. So for direct transfer, you don't really know what works best, so you might as well rank it by which one got the highest score. And you can see here, this has 1, we go 1, 2, 3, 4. So you get like a decent thing to start with, but you don't find the best one to begin with. For order transfer, we go 1, 2, 3, 4. So already for the first one, we've tried the best one. And then for prior transfer, we're not trying any of the values which worked well when we're doing blueberries, but we're saying we think the shape is going to be similar. And so we don't have to try, we wouldn't have to try as many values throughout the entire search space, because we still think if we get to this one and that one, we know what's going on between. And then this is some examples. We did a short survey of what other things sort of related to sustainability you can do with Bayesian optimization. So you can do hyperparameter optimization, and then it sort of becomes, if your neural network or if your machine learning model has a sustainable application, then you sort of tick. But there's also been a decent amount of work on material discovery. So then what you're trying to decide is which inputs do you add into, for instance, solar panels. When you're designing solar or producing solar panel material, what kind of additives do you add in? You can have one about where do you place your wind farms within like wind turbines within a planned wind farm area. And then the point here is that when the wind passes through the wind turbines, the air changes. So if these were one after one another, this one would have produce less power and also get more turbulence. It would have less of a happy time. And then also operating them, because they both where you place them and how you operate them impacts the downwind turbine. And then also you can do it for environmental monitoring, which is where the air pollution comes in. So here we set up our problem as deciding where we wanted to place our sensors in order to find where there's greatest pollution in a city. And the motivation here is that while this sort of state-of-the-art way of measuring air pollution are these big, expensive, hard-to-move sensors, more recently we have these lower-cost sensors become available. And then you could see you can place a lot more of them, and you could think that you could have an ML approach to deciding where we should be placing them. So then within Bayesian optimization, we have modeling our air pollution distribution, choosing where we want to place our next sensor, and then going off, placing it, figuring out what the pollution is. And so we tried this out. We used data from the London Air Quality Network. This is London. You can see that you have different concentrations of nitrogen dioxide. This is just one day, but in different days, there's a slight change in which sensors are available and also where the highest value is. And what we tried was starting out with just a few of these, seeing just a few of these values. How many of them do we need to look at or guess before we find the highest one? And then here I have, often with these kinds of hyperparameter optimization, Bayesian optimization plots, you would have like number of guesses or iterations along the x-axis, and then how well you do on the y-axis. And what we found here was that in one of our Bayesian optimization setups, we were able to do better than random guessing, which doesn't sound like that hard a baseline to beat, but surprisingly often you're sort of knocking your head against it. Yes, that was sort of the example of, you can use it elsewhere than in hyperparameter optimization. And that was the part one. So, any questions?
We applaud here as well for the benefit of you. Everybody's very quiet, but it's time for questions. I actually want to go ahead.
Yeah.
In terms of so for hyperparameter tuning, it sounds really, really powerful. Is there any situations where you might not want to use it, other than like a kind of trivial computation cost?
And I think it really, it's the computation / I guess, waiting time, a bit of setup. That is because I guess sort of worst case is it doesn't find anything better.
Yeah, but it's still getting at least what you had before.
Yeah.
So that's really cool.
Sort of technical thing. So in your transfer learning, how do you look outside the range of your initial, your trial model? Is there a strategy for that, or do you just pick randomly outside? For instance, the last case, I forget the name of it, where actually you've got to move to a different distribution with the same shape, but you've actually got to seek that distribution somewhere in space.
Yeah.
In the parameter space. Yeah, on the bottom right. So you've got some trials there at the bottom right on the axis.
Yeah. So for that one, it becomes slightly technical. But with the way we set up our Gaussian process is we make some assumptions. We embed some assumptions into it about how things are changing, or how smoothly that curve is changing. How many changes do you have? And really, what we're encoding with this is how often does it change direction. So that
gives you some idea of how dense your test points must be.
Yeah, and that's really what we're doing with here. So then it can keep exploring. It is a problem, I think, sort of more so with these ones, because you need to have, here I just said, and then we can try these. But then the next thing you would do would be having then sort of seeded your optimization with these things that work well, then you broaden it out with an exploration. And quite often you would use Bayesian optimization to do that.
Life has a question. Hello, Life. On that, if I read it out for you, I don't know if we can hear people online. Do you want to try and read it, Life?
Yeah, sure. Hi, Sigrid. Really nice talk. I was just, since you looked so much at different ways of optimizing training, something that I've always struggled with is sampling of training data, basically. As sometimes training data can be biased, for example. So your sort of sampling strategy for that might be something you could optimize. And the other thing was, I was curious about optimizing the learning process so that you sort of force the model to look at the part of the data that's most informative in a way. And I don't know if there's sort of measures of that, but that is another. I mean, currently people just randomly sample, right, most of the time. So I was curious whether you thought or come across anything in that area, and any thoughts on it.
Yeah, I think that sort of, in some ways, is slightly. It's hard to embed that directly within this kind of framework, right? Because you want one lever to tweak. You can set up, some algorithm which says how many. You can go and change your optimizer basically, and have that optimizer have a hyperparameter which says this is the proportion of problems that you should sample from the things which we did really badly at. And then you could have that be a hyperparameter which would feed into the normal hyperparameter optimization framework, I think. I think that's how I would approach that problem.
Okay.
Yeah. Okay.
Does
Thanks.
that make sense?
That's other levels of hyperparameters. But yeah, I had a sort of a comment actually. I don't know if it's something that's discussed, but I would have thought there's a net zero aspect to this in the sense that by optimizing expensive, costly training, and doing that more efficiently, you burn less carbon to power our computers.
Yes, so there's definitely that argument, and that especially comes in with the transfer learning, which we don't have to start from scratch, we can do this cheaper. I guess the other side of that coin is I'm saying instead of training your network once and seeing how well it works, I'm saying train it many times with all of these different ones and see what works well. So quite where that ends up landing, I'm not entirely sure.
Yeah. Okay.
Comment on that, Doug. Can you hear me?
Yeah, John, go ahead. Yeah.
There is a downside to that, though. Almost any system, if you make it more efficient, you tend to use more of it. So in itself, it tends to increase consumption.
Well, I think this is. I think it's a good point, John. It's definitely unknown and observed, isn't it? But we can discuss that.
Yeah. I mean, computing is growing because it's got better.
And we can do more with it.
Anyway, but yeah, no, it's a good point.
So Donald, you go ahead.
I was just going to ask, have you thought about hanging on to some of the less optimal models that you get out of this, maybe downweighting them in some kind of ensemble?
That so you have hyperparameter optimization and also neural architecture search, which I mentioned briefly as the thing which I'm not discussing. They both live within a broader field called automated machine learning, and that thinks quite a lot about the ensembling, both in terms of making multiple models and then weighing them by what works well, or maybe being can you predict the errors of your first model? And in practice, that's very ensembling works very well.
Okay, thanks. So we should probably move on, but for the benefit of posterity, should we applaud again?